Hey there, Physics 20s. It's Mr. Jukely again, here to talk to you about Unit 6. Oh, of course you did. Go away. Unit 6, Lesson, I believe 6. I better double check that. Yes, Lesson 6. It's wave reflection and wave interference. Holy, that's a big felt pen. We are going to skip over some pretty big chunks of this. Lesson 6. Some of it is super important for Physics 30. Other parts, not so much. So we'll go through quickly. This stuff, this first little section, I'm going to call it bonus material. There's two types of reflection, fixed end and free end. So very, very, very quickly, if we send a wave pulse and it hits a fixed end that's not allowed to move, it's going to reflect backwards and it's going to reflect inverted. Cool, okay. If we were to hit it and it were to hit a free end, that's a free end, an end that is allowed to move around, the reflected pulse, nope, that's still a fixed end. There we go. Now we've got a free end. An end that is allowed to move around, it's going to be reflected back upright. So it's going to bounce off the wall. It's going to be reflected back upright. Even that is probably more than you need to know with this, so that's cool. This is a bit of an animation, switching from one medium to another. Hey, this is something that's important. What changes when you change from one medium to another? I kind of gave it away there. Speed changes as you go from one medium to another. If the frequency doesn't change, so the frequency has to stay the same, but the speed changes, what's the relationship between speed and wavelength? Well, speed has a direct relationship with wavelength. So if the speed increases, the wavelength increases. If the speed decreases, the wavelength decreases. So that's something that's kind of neat. I'm not going to necessarily show you that there. Not going to go through all of those pieces or all of those pieces. This is where I want to start getting into some more important stuff. The idea of echolocation. This YouTube video, this is actually something that's pretty cool. Just look up Ben Echo. That's not how you spell echo. There we go. Location. This is, as far as I know, the only human being who ever uses active echolocation to see. So this person lost his eyes as a child due to cancer, doesn't even have eyes, has glass eyes that he has to wash out, but he can see by using a series of clicks. It's pretty wild. It's pretty cool. There are a couple animals that do this. So marine animals like dolphins and whales use echolocation. Bats use echolocation. I guess humans use echolocation as well in terms of sonar and radar. But essentially what happens is this dolphin is sending out some sound waves. The sound waves reflect back towards the dolphin, and based on how much time it takes to get there and get back, the dolphin knows approximately how far away that delicious fish is. Cool. Like I said, humans use this. I mean, Ben is a special story when I go back to this guy over here. Like, this is wild. That guy is amazing. A real world daredevil. But other humans use like sonar. So you can go to the store and buy a fish finder. You can go to the store and buy a what's that thing called? A stud finder for in your walls. They typically use some kind of sonar, so sound, navigation, and ranging. When we're talking about this, essentially what happens is we've got a device now that sends out those sound waves. When they hit stuff, they reflect back, and then we get an idea of, say, how deep the ocean is. We get an idea of, so it goes out, hits the fish, some of it will hit the fish and bounce back. We get an idea of where and how big that fish is on our fish finder, which is kind of neat. Humans also use this in ultrasounds. So ultrasounds give out sound waves. They travel through a person's belly, and you can potentially see babies. For me, I had a hernia when I was 19, and they could see my small intestine, which is pretty crazy. Some of them are getting pretty wild. I forget the name of this one, but very, very clear ones. You also have ultrasonic flaw detection. I can't talk right now. But essentially what they do, I just got interrupted by by an announcement there. Essentially what they do is they run the sensor over top, it sends out sound waves. Sound waves bounce back, they pick up on it, and they can tell if there's flaws, if there's bubbles or cracks or anything like that in pipelines and plumbing and different things, which is pretty cool. So we'll skip over some of these. So here's the big idea with this, the really, really, really big idea, something that's very important. if I've got a transmitter and it sends out the sound wave and hits an object, oh, you can't really see that, hits an object, and then that sound wave bounces back, my distance that it travels, my total distance is all the way there, and then all the way back. That's my total distance. The one-way distance, which I'm going to call capital D, is just there. So if you wanted to know how far away something is, you're not really looking for the total distance all the way there and all the way back. You're looking for the one-way distance. And there's a couple different ways that you can do this. It's traveling with uniform motion. So we're just using V is equal to D over T. But this might be our total distance. So we might want to say V is equal to 2 times the one-way distance divided by T, and then solve for that one-way distance, right? And if we actually do that, it'd be V times T divided by 2 is equal to the one-way distance. An alternative would be, we could say V is equal to D divided by T. So again, that's my one-way distance divided by half of the time, right? So if it takes, let's see, 5 seconds to go there and back, it's only going to take 2.5 seconds to go there. So a bunch of different ways you could do this. Just make sure you understand it's going all the way there and all the way back. So the distance is not all the way there and all the way back that we're usually looking for. It's just the distance to get there. Cool. So next thing to talk about here is wave interference, which is our law of superposition. And this is another thing that is fairly important, a fairly important concept. So everything we've talked about so far and everything that kind of makes sense for us is particles, right? Because we see particles, we see actual pieces of matter. When they run into each other, well, they actually collide with each other. They smash into each other. But when we're talking about waves, waves don't really smash into each other. Waves interfere with each other, and then they pass through each other. So I got wave pulse A and wave pulse B. When they get together, they make wave pulse A plus B, so they're moving together. And then when they're done, I've still got wave pulse, let's see, A was still moving this way and B was still moving that way. So they interfered with each other and they passed straight through each other. I've actually got a really quick video for you that's very similar to last time Mr. Dyer and I put together. So this one is constructive interference. And let's put it out here. Okay, so sending a wave pulse one way, and Mr. Dyer sent a wave pulse the other way. That was way too fast for anybody to be able to see, so let's just go ahead and turn this to ridiculously slow speed, and I think it's still coming. Here we go, here we go, here we go. I know you're probably on the edges of your seats. We may have missed the first one. Ah, there it is, there it is. We got the second one. So things that we saw, let me rewind that a little bit. We saw one wave pulse coming this way, one wave pulse going this way, and then when they came together, they made an extra big wave pulse. That is called constructive interference because they are, oh, no, missed something there. Maybe I didn't rewind far enough. There we go. Very nice. Let's even take it back. Okay, this is beautiful. So there's our two wave pulses. They're coming together. I did something wrong there. I'm really bad at this. My apologies. Well, this is a pickle. I know there's another one coming up here. Okay. Sorry about this, folks. There it is. They come together, and then right there they make super wave, and then they move and they spread apart in opposite directions. That took forever to find. I apologize. I apologize. The destructive interference one, let's just have a quick look at destructive interference. This one's a little bit harder to see. So in this case, I've got one crest coming up here, one trough coming down here. When they come together, I gotta slow this down like crazy actually. When they come together, there they are right there. They actually cancel each other out for a very brief moment in time. Oh, I just got better at this, I think. So crest and trough coming together. When they come together, They cancel each other out, so notice there's almost nothing going through here. Skip forward a little tiny bit, and then they continue and they pass through opposite directions. I really hope you can see that, otherwise that might have just been a waste of your time. Yeah, I hope that's not the case. So that doesn't work, which is why I made the videos. So we've talked about constructive interference. Constructive interference is when I have crest with crest or trough with trough, and they make a super crest or a super trough. When we've got trough with trough, and if they're the exact same amplitude, which is what we're seeing right here, the pulses actually cancel each other out, which is kind of neat. So one application of this is noise canceling headphones. I don't mean noise dampening headphones or noise isolating. I mean noise canceling. These are expensive, like $400 for a set of headphones kind of thing. Essentially what they do is they have a speaker that picks up on the ambient noise, and then they actually create more noise that is out of phase and cancels out the ambient noise, the noise that's around, which is pretty crazy when you think about that. You are creating more sound waves to destroy other sound waves to make it quieter. You'd think sound plus sound makes less sound. Not the case with noise canceling headphones. So, okay, let's sketch some resultant waves. This is not going to be the most important thing, but I'm going to show you how to do it anyways. So let's see, what color do I got here? Blue. Blue will work. So we know, and this is our law, all we need to do is we need to add the amplitude from wave 1 to the amplitude plus wave 2, and that's going to equal our total amplitude. So for this first section right here, I'm going to call this my equilibrium position. I'm going to call that 0. For this first section right here, the dotted line, nothing, the solid line, nothing, so you add nothing to nothing, well, you get nothing. That's super easy. For this little section over here, right, I've got my dotted line is still at 0, but then my solid line is at +3. So 0 plus 3 is 3, so it's just going to follow the solid line. Then my dotted line all of a sudden right here starts to peak up a little bit, right? So my dotted line, it goes up to +1. Let's see, +3. So let's see, for this section, I've got 1 plus 3. That's +1 plus +3. Well, that just makes +4. And that's the same for this whole section in here. Then the solid line drops down to 0. So solid line drops down to 0. My dotted line is still at +1. So 0 and +1. 0 plus 1 is just +1. And then they both drop down to 0. This is called constructive, because they're both crests. So crest plus crest, or trough plus trough. Trough would be the same thing but below 0, and it's not actually shown here, so I'll put it in brackets. So constructive interference, making bigger waves. When I have destructive interference, same sort of idea. So 0 plus 0 is 0. And then +3 plus 0, well, it's +3 all the way up to here. But then my dotted line kicks in. Okay, so that's now at -1 and +3. It's literally adding integers is what we're doing. So -1 and +3, well, that makes +2. So that's going to dip down to +2. That's going to be the same all through that section. And then my solid line, look at it, dips down to 0. So all I've got left is my dotted line, and then nothing at 0. So this is, again, destructive interference, where we see the wave getting smaller. I'm not going to make you draw this one. This one's kind of a pain in the butt. If you got the idea from the last two, that's really good. If you get the idea from the practice, it's a little bit trickier. Just pick a couple points, couple key points, and then connect the dots. That's all you really need to do. Maybe I'll show you this one. So nothing, nothing, nothing. Solid line, solid line, solid line until I get to this point, and then I've got my dotted line. So I'm just going to pick this point right here. That is +1, 2, 3, +3, and this one is approximately -1, 2, 3, 4, approximately -5. So +3 and -5, well, that makes -2. So we're going to go up to -2. Cool. Another point that I might choose, let's just randomly choose this one. So I've got +4, and I've got negative, let's see, 1, 2, 3, 4.5. 4.5. So +4. Oh, that would go up to about -0.5. Cool. Maybe I'll pick this point next. So the dark line is at 0. This one's at positive 3.5. 0 plus positive 3.5 goes up to there. Maybe this one next. So the solid line's just above 2. The dotted line is also just above 2. So 2 plus 2 makes about 4. So it's going to go up to there. Oh, 0. So it's just going to go back down and just follow the dotted line. So again, you pick those really key points for this. Really, really, really key points and key areas. Cool. So that's a quick one, which we like. Definitely a quick one. Good job, everybody. This guy's getting more detail, or this person is getting more detail as we go through. Good job. Do a bit of practice with this. The things that I want you to really focus on, like if you understand the constructive and destructive interference, that's perfect to understand how waves can build on each other or like destroy each other temporarily and then pass straight through. That's awesome. That's perfect. The only other piece that I'd really want people to kind of look at and check out is this idea of reflection. So good questions to check out for this are like maybe questions 1 to 5. If you can do questions 1 to 5 from this lesson, you're golden. That's perfect. Anyways, I'll stop talking now. I'll let you get to it. We'll talk to you again soon. Bye for now, Physics 20s.